Hey, my name is Miłosz, and I'm here today to tell you about CQRS and a few other things. So thank you for coming. And nice to see the GoCracow community so big. A couple of words about myself. So I work at GitHub right now as the principal backend engineer, and I'm also co-founder of Freedots Labs. So together with Robert, who you might know from the previous edition of GoCracow, we run a tech blog. We maintain Watermill, our event-driven library, and we also have some online trainings launched recently. So if you want to learn more about what we do, just hit Freedots Tech. And we have those two Gophers to give away today. So there will be a quiz at the end. Cool. So since this is a talk about CQRS, it will make sense to start with some kind of definition, right? And especially with CQRS, it gets tricky. And if you look it up online, you can see those articles that mention that start like, people are often confused what CQRS is about. So let's clarify this, right? So maybe a question to you first. Like, can you raise your hand if you know what CQRS is, what it means? Okay, and if you have used it before in your project, successfully or not? Okay, and the good news is whether you know what it is or not doesn't really matter, because I'm not going to tell you, at least not right away. And the reason is, I feel like definitions are not as useful when it comes to learning about something, about a new pattern, because they often tell you what something is, and maybe they skip the part why you should do it, why it makes sense to use the pattern. Or maybe they tell you how to apply something in your code, but they skip the part when it makes sense to do it and when it's better to hold. Right? So if you just read some definitions about some complex patterns, you might end up with this state when you search for a way to apply them in your project, right? So there's often this thread in the community online. Someone searches for a way to to apply this DDD or CQRS or whatever else in a Go project. And especially in the Go community, there's this notion that those patterns come from the OOP world, the Java Enterprise world, and they don't belong to Go, because Go is simple. It is not object-oriented, and the discussion often ends like this: like, please stop writing Java in Go. We don't do this here. And I'm not here to argue who's right in this argument. Rather, I think it's pointless, right? Pointless discussion, not productive, because what worked for someone else might not work for the newcomer, or maybe how they use the pattern was a bit different. So we are not discussing the same thing. And I think what beats theory and definitions is experience. And I'm sure all of you have some patterns you use in your project. And it's not because you have read a book about them, but you probably used something in one project, and you've seen it work. It solved some issues for you, and then you just continued in your other projects. And I think what's very cool about this is we build this pattern recognition over time in our minds. So you start recognizing some parts of the code, and you can instantly feel like, what's the solution here? Like, maybe you see lots of if statements, and that a strategy would be a good pattern to use here. Or maybe just something else you don't really name, that has no definition, but it works. And I think this is really valuable because it doesn't focus on the theory. It is something you've seen work before, so it makes sense to continue using it. So what I want to share you is 3 stories based on different projects in different companies. And what they have in common is I have used some parts of CQRS in them. But what also they have in common is that I didn't start those projects thinking, okay, I will now apply CQRS here. Rather, looking back at them, I realized this is the common part. And just in case, CQRS sounds to you like some Java Enterprise pattern, I just want to make it clear this all happened in startups using Go as the primary backend language. So the first project I want to tell you about was a project management application. You can think like Jira, but a bit simpler and more modern. And we used a complex backend architecture back then. You might recognize this one. It looked kind of like this. So we had this backend Go server and a front-end client, a single page application, and in between REST JSON API. And there was a database at the end. In this case, it was MongoDB, because back then MongoDB was web scale and the project was supposed to be web scale, so we used it. But it doesn't really matter. The point is the backend was kind of a proxy for the database with some business logic sprinkled on top of it. And as you can imagine, we had some entities in the domain. Since this was project management, our primary entity was a task, which was a big one. If you can imagine a Jira issue, you know how many fields they can have, right? But the point is we used relationships between entities, and we modeled them with IDs. So each entity had its own collection, the database, and they were referenced with IDs between each other, sort of like an SQL database, right? But in Mongo. And in the code, we use this task structure, for example, right? So we had a simple Go structure, and we used struct tags for marshalling and unmarshalling. So we used JSON for marshalling and unmarshalling prompt in REST responses and requests, and Bison for saving and loading entities from the database. If you don't know Bison, it's binary JSON. It's what MongoDB uses for storage, for marshalling. This was pretty straightforward because we had this one model for each entity in the code, and we could just map between the REST API and the database with this struct, right? I think so far there's nothing controversial, right? It's just classic Go code. So we had this /tasks API and this task structure in the code and this tasks collection in the database, and it felt like clean code, whatever this means, because it was normalized, deduplicated. If you wanted to look up a task, you knew exactly where to look for it, right? Whether it was the database or the code. So we were happy about it, but then one day our front-end team came to us and said something like, "Your API sucks." So we were confused, right? And our first instinct was to blame JavaScript. Like, there's probably some client library they use that's not compatible with our API. That's the issue, right? But it turned out the issue was they were not happy about the responses. So our responses look like this in JSON. It's basically the task structure marshaled into JSON, right? Nothing surprising here. But it turns out that our website didn't look like this. It was rather something like this. Right? So we didn't display IDs, of course. We had those more rich models displayed somewhere on the website. And it turns out if all the front-end team had was IDs, they had to reach out to the API with every entity. And if they were nested, there were many of them. It got pretty old pretty fast. And what they would prefer was something like this. So a similar response, but instead of IDs, we would return the full models for every embedded entity. So then they could just reach out to a single endpoint and just map those JSONs onto diffs or whatever you do in JavaScript. So we started thinking, what can we do about it? And we can consider something like, a backend for front-end server in front of the API that would just contact all the endpoints that were needed and just somehow compile this into one model. Or maybe a GraphQL server. But back then, GraphQL wasn't that popular yet. And having another server just for this seemed like a pretty overkill. And there were many of those entities, right? So we wanted a way to not rework the entire system just because we wanted richer responses. So we started thinking, like, can we do something smart? Because we are smart engineers, right? Maybe there's some smart way to approach this. And we found one. Because it turns out if you use the reflect package, you can create your own struct tags. And we had all those JSON and BSON tags in place already. So we figured, yeah, we could just use another one, right? And this is what we did. So we had this entity tag that was used to annotate a field to point to what kind of entity it uses. And then we had a library that uses reflect when marshalling those structs. And the library was able to drop the ID, reach out to the database for the proper model, embed it into the structure, and marshal it all into JSON. So we didn't have to change our struct at all. We just added those annotations, those struct tags, and we were done. We achieved what we wanted. And we felt like geniuses for a moment. But if you just started looking up the Reflect API, please don't, because it wasn't that great in the end, right? Because it turns out if you use a compiled static typed language, and then you use Reflect to do some magic on top of it, we probably should reconsider what you are doing, right? There's probably something wrong. And in fact, it worked, but it was quite hard to reason about and understand and debug and test, right? There was a lot of magic code involved. So even though we didn't have to remodel everything, it wasn't that great solution in the end. But then we had a second chance, because with the same team, we started a new project and we started it from scratch. And we thought, can we start in a different way? And this time we had an idea to just define the responses as they are. So basically, we would have this struct that was similar to the previous one, but the models would be embedded. They would contain the full model from the start. And for the requests, we would keep it as it was, just IDs, because for requests it actually makes sense. There's no need to embed the entire model. And we would just map them between each other. So our request would be mapped to a database structure that will be marshaled to BSON and stored in the database, and then back again to the response structure, which contained all the details of the model. And at first we were afraid of the boilerplate, because if you consider it, there's a lot of entities and a lot of fields, and every time you change a field or add a field or delete a field, you have to propagate those changes to all the end models. So it seems like a lot of work, right, just to have this nice responses. But it turns out it's not really that scary in the end, because if you forget about mapping a field, the compiler will let you know right away, and you can fix it in 30 seconds, right? And compared to trying to understand how Reflect works, this was actually trivial code. So it was a bit of more typing, but in the end, not that hard to work with. I have two takeaways from this project. And the first one is the more obvious one. It's that it's actually fine to have two models for the same thing, for the same entity. And in our case, we had this response model or read model with embedded embedded relationships of other entities, and this request task write model that will be used for saving. And it was fine. And the second one I thought about much later, looking back at this project, is how common it was for us to think of this one model, one entity idea. Like we had this mental model that was so natural that we didn't even consider having two structs for the same entity. We would rather write some magic queries rather than just split structs, because it felt like the right thing to do. And I think it might come from the dry principle, which we learn very, very early, right? And tells us to not repeat ourselves. So we start getting this pattern recognition of, looking at things that are kind of similar but a bit different as something that needs to be normalized and deduplicated. So if we saw two structs that were different by like 3 fields only, our first instinct was to deduplicate and make it one. But it turns out it's not always that helpful, right? Like for behaviors, if you have the same code in your functions, it often makes sense to deduplicate and extract the common parts. But it turns out data models are a bit different, and duplicating data models is actually a useful tool in this context. So then I worked with a project that was supposed to be a control panel for a complex platform. And we were supposed to build a dashboard for the operations team that would serve as help of the platform and let users look up users, filter them by a few different methods, just make some actions on them. And in theory, this would be a pretty straightforward architecture. Like we would have some data within a database, and some API server with some simple client application in front of it, which users could use to reach for data, and that's it. But the challenge was the company went a bit too far with the microservices idea, and our system looked more like this in reality. So we didn't have this one single place to reach out for the data. We instead had tens of microservices, and each of them owned part of the data set we needed to display. So we started considering the options, right? And we looked at what the services expose, what we can use. And there was an RPC API that could work in theory, but there was data we needed. But to look up every possible endpoint just to get what we needed and do it for like a big data set wouldn't really work out, and it would end up probably as distributed monolith at some point. So we knew this is not what we want to use here. And the other thing the services exposed were events. And the events actually contained the data we wanted. So we could use them for filtering, right? But the challenge was we had no way to just search through them from the control panel API. But we started thinking if we can use them to have this single model we wanted, this big database. And we figured we could subscribe to those events and ingest them into this one model. And to avoid conflicts and to not worry about ordering, we would have each event own like a part of the model, right? And we would just keep writing to it as the events came. And thanks to this, we would actually end up with this architecture we wanted in the first place. So we could have this one big database we would filter and search. And in our case, we used Elasticsearch because it made sense for the type of queries we wanted to run. And we didn't have to deal with all those microservices mess. And the interesting part about it was that the reading part, the part that was running the queries, didn't have to know where the data comes from. As far as the left side, the reading side was aware, the data came from a single database. There was a single data source that was easy to query. But in reality, what happened in the background was we had this complex set of events that was ingested to the system to fill this storage. And this split between read and write turned out useful later. And there were a couple of challenges with this approach anyway, like testing, because it's hard to test something if you depend on the entire platform, right? If you depend on tens of microservices with different events that you don't have locally, and the one rule we had about testing our services was that we didn't want any kind of dependence on external services locally, because then our app wouldn't be idempotent as our independent. So the way we solved this was to just emulate the events. So we would have a copy of the events from the production, anonymized, but we out of which we formed like a set of scenarios, and we would locally run those scenarios on the local database, local service, and then just check if the queries work as intended. And the other challenge was embracing eventual consistency, because of the fact that the reading part knew nothing about the event ingestion. The UI was also not aware of it, right? So if something happened in the system and we didn't process the event for any reason, the UI would be outdated for some time until we fixed it. So there was no technical solution here. Rather, we had to make sure that the users who would use the panel would be aware of it. And in our case, they were fine with it. So we didn't have to consider any other options. But it was a challenge anyway to agree on this. So my first takeaway here was that in the first scenario we had separated read and write models that were roughly similar, but in this case we had this huge read model with tens of tiny write models, which was a similar concept but a bit different, and which means that probably you could also have like a few read models with one write model or any other configuration. So it's not that just two models are fine for one entity. It can be any number of them, any types. And the other is that read models can mean like two things at least in different contexts. So it can be this response structure we used before, which was dynamically fetched from the database, the same database that stored the write model. But it could also be an actually separate data store, like in this case, that was populated asynchronously. Which the difference makes a difference when you discuss this with your colleagues, because if you just say let's use a read model, it might not be clear what you want to do, right? You might want to use a different database, or maybe you just want to split the structs. So moving on to the last part. There was a project that was within the e-commerce domain. So you can think like online store but a bit custom. That's why we didn't use just Shopify or something similar. And it started as the lean startup idea. So there was a business idea from the owner, but they didn't know if it would work out, right? So they first hired a freelancer to build an MVP application for them, and it will be just used to prove if the idea makes sense or not, if there are users, there are clients for it. If it didn't, they could just scrape it, right, and not lose time and money. But it turned out it actually worked, and the company started making money on top of this MVP. And once again, this was this boring stack, a single page application and a backend API in a database. And there was one issue with it that, because of fast iterations and no time for like working on tech debt or testing or whatever else, it ended up with this dreaded big ball of mud, right? So if you work with any kind of legacy software before, I probably don't need to tell you more because you know what it is about. So basically, there's this application that makes money and the business relies on it, but at the same time, it is hard to work on because changes are risky. There's no tests, and as the business does great, actually, engineers are not that happy because any new feature requests just get stuck because you can't iterate on this thing. So can you guess what comes next? Hint, it starts with re.
Refactor. Rewrite.
So there's rewrite. And basically goes like this. Okay, we will do the same thing, but in a better technology from scratch. We'll just redo everything as it is, but we will use Go this time, a better database, better front-end framework. But when you consider it, it actually doesn't sound that great because you will spend like 6 months on it or more, and at the end of it, you made no progress. Like the product is in the same place, and yeah, there is some hope that you will go faster, but there's no guarantee, right? Maybe you will recreate the same big ball of mud again. So the other idea is refactor, which also makes sense, right? Like you think, it's just code. How hard can it be? We'll just take this thing apart. We'll just use the Boy Scout rule, fix the broken windows. We'll just make it better over time. It's easy. But then you pick up a task that's supposed to be like 2 hours of work, and you spend 2 weeks on it, and you decide, I don't want to touch this thing ever again. So there's also the third way, which is rethink your life and quit. But assuming you stay, basically the plan is this. There is this old thing that sucks, and we will make it the 0.0. That's great. It will have no issues of the old system. It will bring even more money, more customers, and all we really need to do is migrate, which is like a simple plan, right? Just migrate. And I before that I did a couple of these migrations in different companies, and it actually didn't help me out at all because I knew all of them are so different. You just need to start from scratch, right? And the best part of it is you feel like fixing the plane while midair because the business keeps running, right? And actually it feels funny because the sales team feels great. Like they are super happy. They sign new customers, they promise features, and on every all hands meeting they just celebrate. We hit the next revenue goal, which is great. And the engineering team is like, yeah, let's see. if we can keep doing this like this. So we need to keep the business running, and we have to rewrite or refactor or do something with this thing while not breaking any features. And what we ended up doing was running experiments. So I figured that there are a couple of modules in this application, right? Maybe we can look into one of them and just try some approach. And if it works, we can maybe apply it to other modules. And if not, we don't risk taking a year to do this. And the one module that we knew needed fixing was the products area, which is like products inventory in an e-commerce, because it was used by virtually all other modules, and any feature request we got touched it in some way. So we had to postpone many projects because of this. So I thought, let's look into it. And we started sketching on a whiteboard how it works. So we identified there's this product database, right? And there are clients who buy them, put them into carts on the website, read the description. And on the other end, there's the admin team or operations team who manage those products. So they add new product, they change the description, change the prices, and so on. And this is where we get to the pattern recognition part, because we recognize that we actually saw the system before, right? It's this one. So we have the reading side, the clients who only fetch the products. They don't change them in any way. And there's the admin part that updates them. And we didn't know right away what to do. But from previous experience, we knew that if you have this clear split between read and writes, you usually can use a different tactic for both. They are kind of independent. And eventually we came up with this idea that we can create a new data model for products, which was the biggest pain point. And we would create this 2.0 module for it that would work with this new products model. At the same time, the MVP part will be still working with the old models. And we will just synchronize the write models to the read models. So we would keep them in sync, and thankfully it was possible because the models were compatible. And the best part of this was that we didn't have to touch the MVP at all. Because similarly as with the previous project, as far as the MVP was concerned, it would still use the same models as before. It didn't care where they came from. And in reality, they came from this new application, new models. And over time, as we progress with the migration, we would rewrite the MVP part as well. So we would have a 2.0 client that would use the new models, and we would just get rid of the faulty models altogether. So the migration was pretty complex, right? But thanks to this approach, we could simplify it, because we didn't have to touch the MVP code at all, which was the most risky part. We didn't break anything for the clients. If we broke anything, it would be on the admin side, which is not that bad compared to breaking the user-facing application. And we did the entire thing synchronously, because there was a single database. So we could just update both models in a single transaction. On every change made to the new models, we would propagate them to the old models. But we could just as well use a async alternative. So we could have this similar system with two databases with some kind of message bus or event bus in between, where the read models would be updated over time, like we did with the second project, right? We didn't do it because it felt like having this synchronous would be just simpler and safer, one less risk to take, but it will be possible as well, like this. So my lesson learned here was that this, knowing this separate read and write sites from the previous project, it showed us actually a new way to approach this problem. So changing the mental model about this single entity, single model idea actually helped us see a way out of the situation. And if we didn't apply it before, perhaps we would force it into a single database, try to do it, like try to change everything in one go, which would be much more risky. So in all this, I didn't mention CQRS once, right? So what is it about in the end? So let's go back to definitions, because I told you they are not useful, but sometimes it makes sense actually to have something to work with, right? So CQRS goes back to CQS, which is an old idea, I think, from OOP, that separates methods and an object or a struct in Go into two categories, right? So we could have a command like setName that updates the model, the object, the entity, whatever, and returns no data except for error or maybe some kind of ID. And the other is a query, which is the other one. It makes no changes to the object, but returns some data. Like a setter and getter, basically, right? And CQRS takes this idea a bit further, and Greg Young defines it as the creation of two objects where there was previously only one, and the object he means here is this thing. So in your application, this can be called handler or maybe controller or service, like here, whatever. But there's probably some part in your code where you define the application logic. So there's a set of operations on some kind of entity, like user in this case. So CQRS suggests that you take this thing and split it into two. So there's commands and queries which are separated, like two different interfaces for the same entity. And Greg goes on to say that it forces a break of the mental retardation, that because the two services use the same data, they should also use the same data model. And this is the part that resonates with me, because it means that you can use a different data model for the queries in this context than for the commands. And it is really a simple change, right? Because nothing prevents you from using separate models within the service. But I feel like this is the simple change in the code that forces onto you this new concept of multiple models. Because if you have this interface and you have used a different data model in some of those methods, it would probably feel weird. Like, why duplicate, right? Why use one struct for some method and second for other? It would feel unnatural. But the separation makes it actually makes sense, right? You use this read model for the queries and the write model for the commands. It makes sense. And if you ever heard about CQRS before, there's more concepts mentioned together with it, right? Like polyglot persistence or eventual consistency or even sourcing, which CQRS kind of enables and makes them easier to work with. But they are also not required, to apply this simple change to the service interface. And this might be controversial, but I think splitting the interface is actually not the end goal at all. It is something that forces you into this new mental model, and this new mental model is the end goal. Like, you want to start thinking about this data model as something that doesn't need to map one-to-one with the entity. And you get there by this simple change of splitting the service into commands and queries. And that's all. Thank you.